Welcome to qnawire.
Okay, first of all, what is bromoadamantane? Right? The structure of that's going to be pretty helpful. It's got a really unique structure, if you ask me. Okay. It's pretty fun to draw. And a bromine right here at the top. That is bromoadamantane, or 1-bromoadamantane. Why can't this undergo, let's just go through these one by one. Why can't this undergo SN2? Why not? Well, it's tertiary carbon, right? Tertiary carbons do not work with SN2. We only ever see SN2 with secondary and primary carbons. Okay, that's simple enough. Why won't it work with E2? Well, recall that for E2 to be possible, we need to have a hydrogen which is anti-periplanar to the bromine. That is, assuming these are R groups, right? We need to have this, if the bromine is up, then across this bond, the hydrogen needs to be down. But hey, look, if this bromine is up, there's no hydrogen down because there's a carbon-carbon bond. There's no hydrogen down because there's a carbon-carbon bond. There's no hydrogen down here because there's a carbon-carbon bond. The only hydrogens that could possibly be eliminated while this bromine leaves aren't in the correct orientation, right? We need this overlap of orbitals, antibonding and bonding orbitals to form this new double bond. Okay, so the reason that E2 won't work seems good. Okay, now let's see. Why won't E1 work? Right? Maybe that's a question you might have. Well, if we're going to do E1, recall that we need to form a double bond, right? So in the case of E1, consider the mechanism for E1. This bromine will leave, right? And we will generate, I'll redraw this. Well, not a drop with the bromine. I'm going to need a carbocation here. I'm going to put a carbocation here. But the point is that we're going to have to form a double bond either here or here or here, right? With one of these hydrogens coming off when a base comes in. Sorry, not bromine. A base. That's just a B. Right, that's the idea. Deprotonation and formation of a double bond. But consider what this looks like from the top down. Right? That's what our carbocation looks from the top down. But from the side, we know it's like a tripod. It's a tetrahedral carbon. And these three bonds that it has, right here, right here, and right here, are locked into being tetrahedral by this scaffolding, right? In order to form a double bond, we would have to flatten this out, right? It's like it's currently it's like a tetrahedron, right? And it's like slightly puckered, right? That's what the bonds look like. But we would have to squish it down if we want to get turn this carbon into being sp2 hybridized, right? Or, maybe it's okay temporarily as a carbocation that it not be totally flat. But once we form a double bond, that surely requires that this set of 3 carbon bonds will all have to be in a plane. Well, if they're all in a plane, the orbitals won't align with these tetrahedrally oriented carbons. So the geometry instilled by the scaffolding cannot permit a planar carbon at the top here, or really and none of these carbons with their 3 bonds locked into the scaffolding, right? This carbon is really equivalent to that carbon and that carbon, et cetera, et cetera. They're all locked into tetrahedral geometry. It's almost like you have diamond structure, right? There's no way to squash this down, to squash any of these bonds that are actually puckered up, down, right? So E1 is not possible either. Basically, all that can happen is the bromine comes off and we install a new functional group, a new nucleophile at this carbon.